like saying most of the people have studied or have gone through school, as an example. But when we use the word most, there is an underlying acknowledgement that um, the true population diverges to some degree from that statement. Now, the abstract of the paper and the theme really is dealing with pregnancy studies, particularly the electrohysterography technique, which helps doctors determine whether a pregnancy is going to be preterm or not. And the thing about preterm pregnancies is that there is danger for the fetus involved if the delivery is preterm. Now, a lot of machine learning studies that have done research on using electrohysterography have reported very good results, near perfect results. And we'll go on to see that most of the results are in the high 90%. This paper, the ArchiveX 2001.06 to 96, says that there are certain flaws in how these studies were done and their experiments were done, which makes the results over optimistic. The paper shows why this is a bad idea using a simple toy data set, and then goes on to reproduce the results and show what happens when you properly apply oversampling. So some notes on the data. So preterm delivery before 36 weeks, right? Which is, I believe, the normal delivery time from when the egg and I guess the zygote is formed. So if the delivery is significantly earlier than that, then there is risk of negative outcome for the pregnancy and the baby. The database used in the study has about 300 records of 300 different people, 300 in total. And it can be classified in two types. So if you look at the graph, you'll see that most of the recordings happen around either the 22 to 24 week period and the 30 to 34 week period. So these are like the two broad times when they were measured. And again, then you'll notice, so the y-axis here is the time to birth. So at each stage in the gestation period, like what is the remaining time till the birth of that baby. So with that in mind, you can draw a linear line separating the green and red areas. So green being term delivery, so 37 weeks or around that time, and red being a preterm delivery that increase the risk for the baby. What I don't think is very well represented in this graph, but I took this graph from the paper, is the fact that there is a high skew in the data, like in terms of the green region, right? So there are 262 points in the green region, but only 38 here. You can see that it's more densely populated, but you wouldn't know that it's almost 10 times as much. So here's some notes on the studies and the flaws. The authors identified 24 papers that use machine learning on the data set I talked about previously. And they categorized the flaws that they noticed in these studies into three broad types. One is subsampling. So what you do with subsampling is, coming back to this graph, you would take about 38 to 40 points in the green region, so that it is equalized with the 38 points in the red region. Now, that has some benefits. You are avoiding the oversampling situation, but then you have a smaller data set, and that can result in high variance. Some studies extracted sections from samples. So samples were 30 minutes long and recorded at 20 hertz. So 5 samples each. No, 20 samples each, sorry. And each second. So they extracted like some duration length from each sample, and the authors want that it is important to make sure you don't take validation data and training data from the same sample. And finally, some studies applied oversampling to data before splitting it. The papers, this paper will go on to focus on this third type of error. So some more detail about the studies. In study 37, I'll link the paper as well, and it's linked on the first slide. All records were taken before the 36-week period were removed, and the remaining 138 samples were processed, and a model was built on top of it. And this gave a result, an accuracy of 89%, a validation accuracy. But the problem with this is, just blindly labeling everything as term delivery results in 86% accuracy because of the high skew in the data. 36 use wavelet decomposition. The authors note that this is a useful feature, but they used leave one out cross validation, which is where you train for all your data samples except one, and then you calculate your validation score on just that one sample, and you do that for all your samples. So they are not sure about how robust or trustworthy this score is. And then obviously they use subsamples. Some use subsamples. So this image will show you, this is the toy data set, and it will give you a good idea of what happens if you were to do oversampling, which is basically increasing the number of samples of the smaller data set, smaller classes. So red here, you have fewer in number than blue, right? So if you do oversampling before partitioning the data, which is the top half of the image, you'll notice that you have increased the number of samples, the red samples. So these are just the red line inside transparent samples, the red circles. And so what happens is when you split it after that, you get some amount of overlap between the train set and the test set. So there is contamination involved in this stage. Whereas if you do it after partitioning, which is the best way to do it, or the right way to do it, you will see that only the train the train partition has oversampling, and none of the points or samples that were allocated to the test set have any oversampling or any contamination, because the original points have been separated. That's important here for two reasons, right? First, obviously contamination, and second, if you oversample the test set, like increase the number of samples for the smaller class, you change the population characteristics of the test set. So you are not maintaining a true generalization of the world in that test set. So here's some notes on the oversampling techniques they used. So the paper uses SMOTE and its variants, and I've linked to the library at the end that they used. SMOTE, what it does is basically it creates new classes within the new samples within the neighborhood of the original samples. So it doesn't just like duplicate it. It creates new samples that have characteristics closely resembling the original sets. So what you'll see is if red is the minority class, the dark red is the original, and the brighter red is the new samples created, and they are always created along these the lines. So yeah, One thing to note that the paper mentioned and that was interesting is you have to be careful about how you oversample your data, and that will be determined by how or what model you're using. Uh, Something like clustering algorithm is heavily dependent on the population densities near the margin of your data. So if you were having, I don't know if you can see my mouse, but if you were having you know a straight line, a 45-degree line splitting this data, uh, then the points nearer that 45-degree line would be more important to the margin classifier than the points further away. So you would want to normalize the population densities near that margin as opposed to uh, something else, as opposed to a generalized oversampling. uh, I've conducted experiments, and those experiments were with image data. I have no way of making using SMOT to create synthetic versions of image data, uh, but just oversampling and applying random train time augmentation and mix up allows me to have some amount of synthetic variation. So here's the paper comparison of the results, right? On the left side is the results that were reported by the papers uh, and reproduced, right? So you'll see that they were in the 90 to high 90s and high 80s percentages, and right next to that is um, the results reported when the authors of this paper tried to reproduce their studies. So you'll see with the bad oversampling, which is oversampling before split, you have everything in the 90s. And just looking at this again, so same 24, the paper 24, if you do a proper oversampling, which is oversampling only the train set data, you have 60%, whereas here you had 92%. So that's almost a 50% jump from this because of bad oversampling. And the results are true for everywhere, right? So here, everywhere you have like 90s, high 90s, 80, and for 34 you have 55 here, 88 here, and 91. So that shows you that you should really be careful about how we you oversample or what pre-processing we apply. Yeah. So moving on to my experiments, I wanted to use a completely different data set because I wanted to see if the study is generalizable to other data sets. Uh, like last year, I saw this competition on Kaggle, and I noticed that it is highly imbalanced. I kept that in mind, and so I'll be using this data set. And the challenge was to detect diabetic retinopathy, uh, which is a disease related to diabetes that results in blindness. So here is the distribution of data. You can see it's almost exponential decrease. So you have label 0 with no diabetic retinopathy. You have mild, which is label 1, then 2, then 5 and 4. So it's not like exactly thing, but then decreasing in terms of how the labels are spread. But then there is uh, a very skewed distribution of how this data is. So here's like a practical understanding of what happens if you oversample before your split. So if you oversample before your split in this data set, the number of common files between your train set and test set are 822, which is a huge level of contamination because the train set was like maybe 1200 in length, which is here. So you have test contamination of 73%, and the number of unique files overlapping was about 22%. So you see, this is a huge amount of contamination. You should not be using a data set like this uh, for validation, because it doesn't make sense, right? You are basically just showing it the same images and asking it what it thinks of the data. And also the population characteristics have diverged. It would no longer be in this form. Everything would be the same level as no DR if you apply oversampling before splitting. So your characteristics have changed. So based on my experiments, here are the results. We'll move on to looking in detail at the inferences in the next few slides. But you can see the bad oversampling, which is oversampling before split. You have a 90% plus accuracy, and everything else is in the 80s. Mix up with original without oversampling is 82%, which is interesting. I would have thought that mix up with oversampling would have done better, but I'll share my suspicions regarding that performance in the next two slides. So here are the inferences, right? In the original data set, you'll see um, the the classifier is really good at classifying the most prevalent class, and also the second most prevalent class, but everything else is not so good, especially class number 3 here, which is only accurate 10% of the time. Class 4 is 50% of the time, and same with class 1. So this is the original data set. And if you apply the bad kind of oversampling, you'll see that everything here is 90 in the 90s range, except the second class, which is still pretty high in the 72 range. It's fallen from here, but then again, we cannot use this because there's a lot of contamination involved. With the correct oversampling, you'll see that the class 3 has improved drastically, like about 300% from 10% accuracy to 44%. And the validation for this one and the original data set are the same. So you can actually compare these characteristics. Again, even for class 1, it's improved from 52% to 71% with oversampling. And yeah, there's a marginal increase in class 4, but it's still increased. And in the next set, we have mix-up. So we have the original data set again, just for comparison. And we have mix-up plus the original data set. So here we have again 93% accuracy here. I mean, sorry, 98 accuracy here. But here's the interesting thing, right? So everywhere else, it has fallen from 80%. There is a fall in the detection accuracy of the class 2. But in this, and I suspect this is where the 2% comes from, you will see that it has actually increased from 80 percentage or below to 84%. My suspicion here is that there may be noisy labels associated or noisy images associated with the second label, like maybe it is 1 and it was assumed to be 2. And what mix-up does here is, like, by taking your class 2 image and mixing it with a class 3 image or a class 1 image, it removes a lot of that ambiguity by saying that, okay, there are characteristics of both class 2 and class 3 in this new composite image. So that helps the model learn. And mix up with oversampling does a lot worse here in the second class, because I suspect that there are a lot less instances where class 2 has that ambiguity resolved. But otherwise, it is doing better in class 4. Yeah. That's about it. If there are any questions, I'll be happy to answer them. I'm sorry if I went really fast. I might have an eye. I didn't realize. Any questions?
Did you do any experiments with, instead of oversampling the underrepresented classes, you undersampled the overrepresented classes?
No, I've not done that actually. That would be an interesting study. I have not done that. I stuck to oversampling and just doing the original data set. Here. So just original data set. So a fraction, a percentage of the original data set, and oversampled. But yeah, that would be interesting. How like removing those classes. So I guess class number 2 and class 0. What would happen if we cut them down to maybe 500 samples each? That would be interesting. Yeah. Any anything else?